So next speaker is Kalle Åström, that most of you have probably seen before. And Kalle is going to talk about machine learning for the analysis of images in digital pathology.
Thank you very much.
Tricky word in the afternoon.
Yes. I'm going to start out with Verklighetens folk och Henrik Wide again. And he has a song that says, Googla inte dina symptom. And I thought it was relevant for the previous talk. So now we have a much better solution for searching for your diseases. I will try to talk about how to analyze microscopy images in digital pathology for understanding prostate cancer samples. So similar to before, when I say we, we're going to present results from several papers from many researchers here in Lund and Malmö. So there are many researchers, both from math and from medicine, involved in these projects, and I have probably missed a few as well. So when I say we, it could be any one of these that have done many different things here. So the overview of my talk today is that first I'll talk a little bit about the math department, where I'm from, about what we're doing. I will talk a little bit about artificial intelligence and machine learning at Lund University, and then go into the questions concerning classifying the so-called Gleason grade score from samples of the prostate. And I will talk about a few different topics, a few different attempts we've made trying to do this automatically. And then we'll summarize in the end. But just to give an overview of where I'm from, so I'm working in the math department, so it's a building just across the street from where we are now. In the math department, we're doing traditional mathematics, statistics, numerical analysis, so lots of different topics within these areas. And we've been particularly successful within partial differential equations and, say, computer vision and machine learning, so many prizes and stuff. In particular, Lars Hermander got the Fields Medal in mathematics in 1962. And the kind of things that we do within computer vision and machine learning ranges from trying to do 3D understanding, 3D modeling from images. It's decision support, e-health. There are questions concerning, say, traffic safety. Can you determine how safe a traffic environment or an intersection is? How many accidents will there be per year? Machine learning to understand questions in agriculture, smart cities, genomics, lots of different questions. Questions where you have lots of data and you have different modeling and machine learning kind of questions on top of that. These tools, the machine learning tools and computer vision tools, they are often used in many different applications, as we saw here, totally, where you need different competences. So therefore we work together with lots of different departments, but also together with many companies on master thesis projects or industrial projects and so forth. And we've also had a number of startups from the math department, and I think compared to math departments in Sweden or in the world, I think we're very competitive in that regime. So artificial intelligence and machine learning. This is a graph showing of different types of topics that people usually consider when they talk about artificial intelligence. So this is like computer vision that I'm doing quite a lot, and machine learning. But we also heard about natural language processing today, robotics. But it's also important to think about how artificial intelligence and machine learning, how that interacts with society. So the economy of artificial intelligence or the ethics of artificial intelligence. These are topics that I think we are already doing at Lund University, but I think we need to do more research on that. So if we look at the big picture of artificial intelligence and machine learning, I think already at Lund University, since it's such a broad and complete university, I think we have most of these parts already. There are many courses already on artificial intelligence, machine learning, but I think we need to develop a few more. There are lots of master thesis projects and innovations already, but perhaps the part where we need to work more is how can we do also courses for industry and for society as a whole. So therefore we've formed an informal network, AI and ML at lu.se. So it's just recently formed. Matthias and I and several others here are involved in trying to start up this informal network. There will be a first workshop the next Tuesday, the 29th of May. And the goal is to form a tighter network at Lund University, but also to interact with society and industry, and to work together to do new projects, courses, and basically to know more about each other and to be able to do cool new research together. Okay, that was the background, the introduction, and the advertisement for this new network. So prostate cancer. It's a cancer that many men will be diagnosed with, and it's something that's very common if you compare it to other kind of cancers in the world. And there are different types of investigations you can do. We've already heard about Lars Edelman talking about investigations where you actually don't take out anything of the prostate. But there are two types of examinations that the pathologists do. One is that they inject a small biopsy needle and you take out a small slice of the prostate. And then you fixate it and you stain it and you take images of it. But sometimes you actually take out the whole prostate, and you might do the same thing. You might still fixate it and stain it and take pictures of it. So we have biopsies and you have the whole prostate. The prostatectomy is the operation where you take out that. And then there are quite a few done every year at the University Hospital here in Skåne. And how do you understand, how do you grade these? Well, the best prognostic and predictive marker is still a grading system that was invented by Donald Gleason in 1966. So originally there was a 5-grade score, 1, 2, 3, 4, 5, but now it's been revised, so there's like benign, and then it's 3, 4, 5. So there are 4 different grades of this Gleason score. And the in the benign images you see a lot of structure, you see how the cells form different glands, but in the more aggressive cancer grades the cells do not form in a functional gland, so they sort of just grow randomly. But it's a grading system, so there are no strict borders between the different grades, and you will not get consensus. Different pathologists will make different classifications. So it's subjective, and there's quite low reproducibility, but still it's the best thing that we have. So the fact that it is difficult to grade, that it's quite subjective, makes the need for some standardization and for automatic diagnostic systems. There's a great need for that. So that's what we're trying to do. Another reason for why this is interesting right now is that if you compare to X-ray images, X-ray imaging has been digital for many years now, but pathology has been analog until now, basically. There are many reasons why that is, but one reason is that these images are so huge. They are like 100 megapixels or 200 megapixel images. So just the techniques and storing and stuff like that has been difficult. But now we're at the point where it's becoming easier and easier. So we have these 4 grades. So if we try to classify that, we're going to our first attempt was to generate a small database where we had images and where the whole image was of one consistent grade. So it's not like we take a huge biopsy and this part is benign and this is 3 and this is 4. We actually cut out small pieces where that whole image was either benign or 3 or 4 or 5. And it's a good starting point to try to understand and solve this problem. So we had then, I think in the first attempt, we only had 200 such images, where roughly 50 each of these classes. And we made several different attempts earlier on using traditional, older machine learning techniques, but a few years ago we did it using deep learning. So basically you throw in an image of a specified resolution here, and then you have a deep learning network with lots of weights here, which you try to figure out what they should be, and you end up with 4 numbers, one for each one of these 4 classes. So if the first one is highest, then you say it's benign. If the second one is highest, then you say it's Gleason grade 3. And then you try to optimize all of these parameters so that you get as good precision as possible on your testing set. So typically, when you optimize, you start out having a large error, and then you get smaller and smaller errors on your training set. But when you then test it on a validation set, you get slightly larger error, but still no sign here of overtraining or something like that. So quite reasonable. Usually these images which we test on, they are bigger than these specified cutouts. So given a slightly larger image, which is supposed to be of just one class, you can classify different patches and then let them vote. And when you do that, and you take the voting sort of per image, you actually get a final score which is errors which is slightly lower. So something in the order of 92, 93% correct we got on these first tests. So that seemed promising. One problem is that when we developed this, we had all of the images from one hospital, say from a hospital in Dublin that we worked together with. And then when we tried it on images from Lund, it didn't work at all. So if we train it on Dublin images and test it in Lund, then we got like 32% correct. If we train it on images from Lund, we get 75% correct on the Lund images, but we get only 60% correct on the Dublin images. So there's something strange going on here. And what is that? It's the fact that the process of getting from the sample to the images involves manual staining. You take the tissue and you fixate it and you have these staining colors, and the way you do that in different hospitals are slightly different. We used to do this. We do it for 10 minutes and then we do this for 5 minutes here. We have this color staining procedure. So within a hospital you can be quite consistent. So these are examples of images from the dataset B. And these are examples of images from dataset A. And you can see, as you can see here, these are slightly darker and these are brighter. These are slightly more textured and these are more slightly low resolution. So that is a problem. So what can you do? Well, you could do so that you sample images from all over the world, from every hospital. But it's a huge effort getting images from all over the world. So we're starting to think about how can we do things to normalize the images or do something so that we could train our classifiers on one hospital with a large data set and then perhaps use the other hospital images by first sort of normalizing them or doing something. So that's what I'm going to talk about now for a few minutes. Different attempts at trying to normalize images. Okay, one such attempt is built upon having a slightly different architecture. Again, you throw in an image and you do a few layers of a deep convolutional neural network, but then maybe you upsample it again, so that the end result is not a class. The end result is an image. So one idea is that maybe we could do some classification of the different parts in an image. Maybe we could classify what is sort of white background, what is something called stroma, what is the cytoplasm, and what are the sort of cell nuclei. If we could do that and then build a classifier on that, then it would perhaps be more robust to changes in coloring. So we made some research on trying to do that very well. So we've manually annotated some images to get some ground truth. We allowed for some 2-pixel wide border between different classes. So having a slight errors in where the classes begin and end shouldn't matter as much. And then we tried different architectures for doing this so-called semantic segmentation. And as I said, usually you start with image, you have some layers to form a smaller image, and then you upsample them to form a bigger image. But sometimes you have an architecture where this is the subsampling part, this first part, and this is the upsampling part, the second part. But then you also transfer some information across here, sort of directly from here and here. So I mean, these are different ways of playing with how these deep learning architectures are made. And we tried doing different variants of this. So this is this so-called U-net structure, but slightly different variants of this one. And also to expand upon a data set, quite often you try to do different types of data augmentation. So for instance, if you have an image, you might rotate it and flip it or scale it or do something so that you sort of artificially make more data that you have ground truth for. And these are some results of that part. If this is an original image, this is ground truth, and this is like the result of our automatic segmentation. And it became, I mean, reasonably well. It's not perfect, and it could probably be improved. And if we look at the confusion matrix, we have quite good results here. We've actually not made any progress in getting better classification using this system yet, but this is one of the avenues which we have tried. Another attempt has been to try to actually split up the raw data into the 2 different staining colors, because you're actually staining with 2 different staining pigments, you could say. So you could try to split up this image into how much does this image contain of the first color and of the second color, and then use these 2 channels as an input to the deep learning architecture. So that's called stain separation. So we tried to make different methods for doing that and then enter those into the deep learning network. And then we've also tried different sort of standard methods for trying to normalize the images just by changing the color, so the color correction. So these are more like image processing type of methods. And a third attempt we've tried to use is to use so-called autoencoders. So in autoencoders, the game is that you have the same architecture as for this semantic segmentation. You have the original data, you do some deep learning processing to get some sort of lower dimensional coarser data, and then you upsample it, and you train the whole network so that the output should be identical to the input. And then you hope that this middle layer should be useful features to do the classification on, and also that this one should have less sort of staining color influence on that one. So that's the third attempt. And we tried to evaluate all of these different ideas. And again, the idea is that we have a large data set from here from Lund and Malmö, which we do the classifier on. And then we have several smaller data sets from different hospitals. So we try to convert, when we do the validation, we convert them into sort of Lund-like images and then classify them using the Lund trained data. And we try to get that performance up as high as possible. And the Lund data is the A1, so we expect the numbers to be high on these ones because we're actually training on the Lund data. And these are the results when we evaluate on the other hospital data. And the autoencoder is, right now it's the sort of the best one. It's not really good yet, so we're still searching for better methods to try to solve this problem. And one of these methods, the one that's looks really interesting and promising, is called cycle GAN. So cycle GAN is an idea that you have two sets of images. So think of these as the Lund images and Linköping images. So then you try to train all of the weights in a deep neural network that convert from, say, Lund images to Linköping images. You also train a network that tries to convert from Linköping images to Lund images. And then you also train a network that could classify, is this a real Linköping image or is it a fake Linköping image? And you train a fourth network that tries to classify, is this a real Lund image or is it a fake Lund image taken from Linköping? And then you optimize all of these four networks at the same time. And you want, when you go in the circle here, you want to get the same thing. Or if you start here and go in a circle, you want to get the same thing. But also you want these to make fakes that are as good as possible, that can fool the discriminator here. And you want the discriminator to be as good as possible to figure out what's right and wrong. And then you keep your fingers crossed and you hope that this converges to something useful. So the ideas are taken from, there are several papers of picture-to-picture transfer, but this is one of them, the cycle GAN by Xu et al. And there are some, when it works, it's really impressive. So these are some results of converting zebra images into fake horse. And this is, so it's taken from their paper. And this is a real horse image that's converted into a fake zebra image. And sometimes it totally fails. But, and these are examples of real apple images converted into oranges, or orange images converted into apples. So you can see how it changes the texture and does stuff, but it keeps the sort of the geometric configuration of things. So we apply this now to our Lund, Linköping, Belfast images. And so this is a Lund image that has been converted by cycle GAN into one of the other hospitals. I can't remember now which one was which. So you can see how it's slightly darker, it has slightly different texture. This is going more towards Lund Malmö images. You can see it becomes brighter and a little bit different in texture. So it looks promising, but there are some things that we are concerned about, and we haven't really fully tested it yet. And that's the fact that it doesn't only change the color and the shading, but it can actually also add cell nuclei and change the images. And that's not really what we want. So for instance, this is an example of an image where you can see there are more cells here. So we have to be careful that we don't change from Gleason 3 to Gleason 5, because maybe there are more Gleason 5 in one of the hospitals or something like that. So I think it's promising and it's really interesting, but yeah, have to do this with care. So to wrap this up, what we've also done is that we've tried to put all of this together so that given these biopsies, we run it on the whole images and not, both segment out the different pieces and classify them as benign Gleason 3, 4, and 5. And then we want to evaluate that with pathologists. We also would like to do this for of whole slide analysis, but right now we're doing the evaluation on these biopsies. So here's a manual segmentation done by one pathologist, and here's one done by another pathologist, and this is done by the system. So typically what happens is that manual annotations are more like simplified and coarser, whereas the automatic system has the time and energy actually to annotate in very great detail. But still, when we compare the difference between two pathologists and between the pathologist and the system, we've made several different comparisons, but here we've compared the area covered by cancer in a sample. So this is how large area is the cancer by the algorithm compared to the pathologist, by algorithm compared to pathologist 2, and pathologist 1 compared to pathologist 2. And then we get similar types of correlation scores. So that kind of tells us we're in the right ballpark. We're doing something that is reasonably good. So we think that we can go on and do more evaluation to see how this could actually be used in practice. So with that, I'd like to end. To summarize, we've made several different, started out with small patches, then trying to do that for whole things where we do segmentation and classification. We've run into this problem that we have different staining at different hospitals, so that has made us look into these different ways of handling the staining variation. We made prototype systems and we evaluated against pathologists. There are interesting future research here is to work more on these staining normalization, and also to work more on how to explain the results of the automatic system. Why did I say it was Gleason 4? And there's interesting research here going on trying not only to get an output, but also to try to explain for a human why did this classification, why was this segmentation and classification done? And that's something that we would like to work more on. But with that, I'd like to end, and I'm happy to answer questions. Thank you.
Very impressive work. Thanks a lot. I was just thinking, so you have two data sets from two hospitals, two sets of pictures. So if they can be somehow digitized, so quantified somehow, so you have two matrices, X and Y. So you can sort of extract a common variation from these two matrices, or calculate like covariance matrix of X and Y, and factorize this common variation. So those factors will be your common features, because you want to extract common features and train your classifier on the common features, right? Yeah. So like, wouldn't it be like quick and dirty way to, instead of building autoencoder should give you approximately the same. Yes. You're sort of doing also dimensionality reduction in order to extract common features. Yeah. But like just a simple extraction of common variation from two data sets and factorization of this common variation, wouldn't it give you common features?
Yes, I'm not entirely sure I understand, but what you could do, if you want something that's coarse and simple, is that you could take each pixel and look at them as RGB values and as a 3-vector. And then you take all of the pixels from all of the images from one hospital, and then all the pixels images from another hospital. And those could be slightly different in sort of a 3-dimensional space. And then you could try to get the transformation between these sort of factors. That's sort of a color normalization that you could do. Or you could try to, if these are, actually since these are only two stains, these 3D pixels, they typically are on a plane, so you can find this plane, and those would be the color stain. Those would be sort of the pinkish or bluish vectors in this space. So you could do something there. If that's what you said, I don't understand.
Can you represent your pictures by just metrics?
So the picture is usually then a tensor. So it's 3 matrices, one for the red channel, and one for the green, and one for the blue. But I think what we're trying to do also, these coloring, these autoencoders, we've tried to extract what sort of the structure. You have structure, which is like the stroma and the nuclei, and what is like the color information, staining information. If we could separate those in a good way, that's something we've also tried to work on, but
interesting.
To some extent.
Thanks a lot.
mean, just following up on that, to see if I've got the right sense of what you're saying. I mean, so for example, if 10% of pixels were twice as bright as half of the pixels or something, there's a structure in an image. And I guess the point is that kind of a property or something like that could be independent of whether I stain for 10 minutes and he stains for 15.
Yeah.
I guess that's the point, right? So is there some underlying mathematical property of the pixels that's independent of what's been done to the image?
I think that makes sense. So there is structure there. And if you have two images from two different hospitals, I mean, they also differ in structure. If one is just white and a little bit of stroma and cell, and one has many cells, then they were different. That's where we thought that these segmentation into stroma and nuclei would help us in doing the stain normalization better. But I think there's lots of opportunities for doing improvements here. Yeah.
There's this concept of image registration where you try to have a sequence of image and then you match them to an original process. So the major example that I've always seen are you take a brain, you slice it into very small pieces. So each slicing process distorts the brain, right?
Yes, so then different slices here.
Exactly, yeah. And then you make it durable, yeah. So you add some chemicals that again diffuse the actual brain, and then you take the image. So now you can try to reverse the process because you know what has physically happened. So you can write down a mathematical model of how the knife that cut the brain distorted it, so that you can then, well, transform this back and get a very nice, smooth 3D representation of a mouse brain, for example. Couldn't this be something that could be used here too, that you describe, that you write a model down for how is the different staining process affect the image mathematically and then try to reverse that process?
That's interesting. I don't think the 3D thing is... I mean, you could slice things in 3D here as well. But we've normally only worked with one single 2D slice. But definitely on the lines of trying to understand and model the staining differences in staining process, I think definitely you could do something there, and that would be interesting.
So there's a huge group in Lübeck on the other side of the Baltic Sea that works on this.
So we should talk more about that.
I actually have a question myself. so the one of the first parts of your talk, when you trained your model and then it worked good within the data set, but then you test it on another data set and the performance dropped. So the question that you was the different kind of staining that could make a difference. My question is about gold standard. So were the same annotator in the two different data sets?
That's a good question, and I honestly don't know whether they were reclassified or whether also the gold standard was from the different hospitals, because
that is something
that's a huge factor here.
Yes, yes. So you might have a good system, but the one system was trained towards one annotator, and the other, and then it doesn't work if you want to use another annotator.
I honestly have to check that, but yeah. Good question.
Okay, let's thank Kalle one more time.
Thank you.